Hello everyone, I'm Maëlle Martinez and today I will introduce you our webinar on gated imaging. Thank you for attending it. So to begin, just a quick company overview. New Imaging Technology is a French sensors and cameras supplier. It is one of the leaders in InGaAs and CMOS sensors for providing SWIR and visible solutions. And all the products are known for their high dynamic range of more than 120 dB. The products are used in several applications such as industrial vision, surveillance and defense, and also automotive. So for this webinar, we will listen first of Yang Ni, the CTO of the company. We will present us the operation principle. Then Nicolas Baron will speak about the new opportunities provided by a gated imaging feature. And at the end, Frank Christnasher will present a real use case by detailing his own use of gated imaging. After the presentation, we will have a question and answer session. So don't hesitate to write your questions directly online, thanks to the tool. And thank you. So Yang, first, we are listening to you.
Thank you very much. So I'm Yang Ni, and the CTO for the company. And so I just to give you a simple overview of the operation principle of gated imaging system. So basically a vision is to see what and where in the 3D dimension. And so the 3D dimension scene is projected to a camera. This is a compressive projection. So we will see everything in a 2D way. So sometimes we would like to simply see things in some predefined distance range. So in this case, we have to descale the object before and after this predefined distance range. So to do this, we have to use active imaging illumination. That means we shine the short optical pulse to the scene and capture only the reflection from the predefined distance in the 3D distance. So to operate this system, we need two major components inside. So one is the very high peak power light source. So it is normally a laser source with some particular wavelength. And the second one is a fast shuttering camera, which can make a very short exposure time with a very precise shuttering phasing timing compared with related to the laser emission. So obviously this kind of active imaging system can be operated in virtually all the spectral range, but we have particular advantages of a 3-band for this kind of imaging system. So firstly is this kind of gated imaging is a reflective imaging system. So when you use different wavelengths, the reflection coefficient of objects change dramatically. So by using a 3-band, we can get very natural scene, very similar to the scene captured by using black and white CCD or CMOS camera. So it's much easier for a human observer to interpret the scene after capture. And the second advantage is the 3-band has a better transmission in the atmosphere. So this permits the laser light be projected far and get image with more sharp contrast and also less visual diffusion to the camera. And the third advantage is the eye safe issue. And if you use, for example, The most of traditional active imaging system is using image intensifier tube by getting the photocathode with a fast pulse. And this kind of system operates normally in 800 nanometer wavelengths. So you can see from this graph that in this wavelength, the eye safety threshold is very low. So basically, you can only tolerate 1 microjoule per centimeter square. This is very low because simply this wavelength can be focused on the retina, which is a very fragile part of a human body. But when you move to a 1.4 or more nanometer wavelengths, you can see that this threshold is raised about 1 million times. So that gives almost absolutely safe operation for the most of laser source used in this kind of system. So the basic requirement for the camera in this kind of application is basically the shutter open-close efficiency and also the shutter open-close speed. So this is very related to a particular sensor design and also physical structure used inside. So not all the cameras on the market can do this job. So basically we need to use very short exposure time in the 3D gated imaging. So that means the shutter open-close speed should be very high. And also because we need to scale as much as possible the rate of diffusion before and after the predefined distance range. So we need the shutter be very efficient. That means when it is closed, it should be almost insensitive at all to light. And when it's open, and should be very efficient to collect as much as light as possible. So to fulfill this requirement, we carefully design our PDA and also readout circuit by special cares inside the structure, and also using probably physical structure, physical principles to accelerate the shuttering operation. So, for example, we have quite a special pixel design which ensures very fast pixel reaction time to permit a very short exposure time. And we also carefully optimize the signal pace inside the ROIC to reduce the RC effect in the circuit, to get not only high speed, but also shutter uniformity across the array. And also we have some dedicated photodiode array which support high dynamic range, and that is also important in active imaging, because when you illuminate a scene in function of the distance you choose, it could be far, it could be near. So the laser energy can change dramatically. So all this gives a very good result in shuttering and also in dynamic range. So that is the real measurement of this performance from our image sensor. So we use a very short laser, which is a little bit less than 5 nanoseconds, and with only 4 watt power. And this laser is shifted in time, and then we observe the sensor output to determine the shape of the shuttering operation and also the rising and falling time of the shutter. So we can, on this example, show you that the exposure time can be cut down to almost 100 nanoseconds. This corresponds to only 15 meters in the 3D space. And the rising and falling time is about 20 nanoseconds. This gives you only 3 meters distance of ambiguity in distance definition. So this good performance permits you to get a very shallow slice in the space, and also very sharp definition of this slice in the space. So give you a better 3D reconstruction result further. So here is a live demonstration of this system. and we have a garage. Inside the garage, and we shine a constant laser on the scene at first. So you can see almost everything in the garage. You can see outside the door. You can also see things inside the garage. So this just shows the widening range of the sensor. And also you can see that the numeric plate, there are 3 placed at different positions in the garage. So the garage is not quite big, so you can see the effect of the shutter precision and the speed. So by changing the phasing, the phasing relation between laser emission and the shutter of the sensor, we can highlight either the close plate or the further plate. And also you can see that the outdoor scene is almost completely removed. So this gives you a much better image to interpret and to separate objects from the surrounding in the image. So that is the operation principle for the active imaging. So I left the word to Nicolas Baron to talk about some applications around this system.
Okay, so thank you, Yang, for this explanation about the gating imaging principle. So now, before talking about application and markets, let's first take a look on the value chain of the gating imaging devices. So when we first take a look on the gating imaging devices, we see a first stage made of camera producers. Those companies are making cameras in-gas, with in-gas sensor, with high shutter efficiency and very sharp exposure time control. On the other side, you have the laser manufacturer able to provide a laser source, pulse source at a wavelength of 1.55 micron. So those suppliers are currently selling their product to a second stage of the value chain made of integrators and end users. So what we see at NIT, we see a lot of demands coming directly from the end users. So those end users are buying the cameras and the laser, and then they integrate by themselves, because mainly depending on the very specific application, they need to develop their own system. There are not so many integrators today on the market able to provide a full standalone solution with gating imaging compared to LiDAR, for instance. In the market, you have plenty of companies able to offer LiDAR solution or time of flight. But in gating, I think it's very, very different, and it's maybe a new opportunity for companies. So what are the new opportunities you can expect with gating imaging? So first, let's take a look on the main feature of gating imaging. So first, with gating imaging, you are able to perceive in very severe conditions, meaning you are able to see through snowstorm, dense smoke, fog, or heavy rain. Second, you are able also to detect targets by suppressing the background and the foreground. And last, with the gating imaging, you are able to enhance your observation by estimating real distances. So with these main features, we highlighted here 3 main applications. The first, and maybe the newest application, is probably the automotive market. So we are here talking about the autonomous vehicles with level 4 or level 5. The second application is the defense and the military. It's probably the oldest application using gating imaging principle. And finally, we get the surveillance and security. So here we talk about high-end security and surveillance application, mainly coast surveillance and also the long-range surveillance application. So first, let's take a look at the automotive and the autonomous vehicles. So as I mentioned before, we are talking about level 4 or level 5, meaning that the car is able to drive in all weather conditions and all road conditions without any help from the driver. So here the challenge is how to acquire robust information in all weather conditions without any help from the driver. Of course, you currently have some existing solutions like LiDARs or infrared detectors, but those technology solutions are just bridge partially the gap, meaning that those solutions have limitation. For LiDAR, it's about the distance range. So currently, you can find LiDARs with capability of 15 meters, 80 meters, but if you want to go to 200 or 300 meters, then you need to increase the laser power, and then you get some issue with eye safety. The infrareds are limited because of some contrast lost when facing to snowstorm or heavy rain. So a typical use case to illustrate what the gating imaging can bring is a highway with vision capability at 200 or 300 meters in dense smog, like the picture you see on the right side. So without gating imaging, in a very similar condition, let's take the snowstorm example, the target useful signal of the vision system is completely blurred among the parasitical light due to the backscattering effect of the upfront snow particles. So at the end, you are not able to clearly see or clearly distinguish the orange car or the blue car. But with gating imaging, you are able to select exactly the slice, and you are able to clearly have a contrast image with the orange car and the blue car, and you are able to remove completely the backscattering and avoid a gray out effect. The second application we noticed here is the security and surveillance application, where the customers want to focus on a very selected area and to identify a target. So the challenge is to acquire images of a perimeter target through the ambient perturbation or interference. You want also, in this kind of situation, you want also to have identification capabilities while being robust to any ambient light and external parameters. So with gating imaging, you have the best of the both worlds. You have the observation capabilities of active imaging, but also you have the discretion of passive imaging. So by having a typical situation in long-range surveillance, where let's say that you want to focus on the boat on the background. So if you don't use any gating imaging, what you get is the picture you see at the bottom of the slide. So you can only see the swimmer. The signal coming from the boat you want to get on your picture is completely blurred on the scene, and you don't have any contrast related to these targets. If you use a gating imaging, you are able to select only the slice in the scene, and then this useful signal is completely isolated to increase the image quality. And finally, the last application we highlighted here is the defense and military, one of the oldest applications using gating imaging. And in this case, let's say the main feature, one of the requirements of the customer is to be able to have an instantaneous 3D modeling of the environment. So people want to obtain information of the surrounding environment without any intrusive solution. They want to map, for instance, the hostile environment of the enemies in a very secret method and at a certain distance. Once again, you have alternative methods like radars available on the market, but those solutions are suffering from low resolution, and gating imaging is able to overcome the existing limitation. And the principle is based on tomography and time of flight measurements. So by having a different slice, a different gate, and by moving step by step the delay between the shutter and the pulse, you are able to move the slice and then to reconstruct the 3D map of the scene without any intrusive and without any UAVs or things like that. So now I think we need to see concrete and live applications. So I'll let Frank Krisnacher from a very famous institute of Saint Louis, very pioneer about gating imaging, and we'll talk about the real application and the real use case of gating imaging.
Okay, so my name is Frank Krisnacher, and I am from the French-German Research Institute of Saint Louis. Our institute is making fundamental research in the domain of armament, and in our group called Advanced Visioning and Processing, we are dealing with different optronic technologies, among others active imaging. So on this image you can see a result of one of our first active range-gated active imaging system, which shows on the left side the capacity of this technology to see through smoke, for example. So on the left side you have an example of gated imaging, and on the right side you have an example of non-gated imaging. We are working on active imaging since more than 10 years, and as you can see on this slide, you can see some of our different systems that we developed in the past for different applications. So as you can see here, we are using different wavelengths in order to address different applications. The wavelengths are ranging from the visible spectrum, for example, for underwater imaging, going through the near infrared at 800 nanometer for police or military applications, and going to the sphere, which has the advantage to be in the A-safe domain of the spectrum. Here at the right side you see two portable active imaging systems which are integrating NIT sensors. So as you can see here also, we can address a system from which have a range capacity of about some hundreds of meters, to systems which have a range capacity overcoming 20 kilometers. With this system we are addressing security-oriented application, and as you can see here, we made in the past a system for the police of Paris, which is used in soccer stadium to see the people which are using fumigating smoke in stadium. And as you can see here, it is very easy to see them behind this smoke with active imaging. So military application, of course, is using to make night vision, but due to the fact that we are illuminating the scene with a laser beam, you have a lot of different advantages by using this technology. So you can make sniper detection. You can see here the pointed optic detection. You can see that we are able to see the pointed optic, yes, by the very high level reflection on the optic. Active imaging is also used to see through military smoke, and this is an example of a very strong density of military smoke, where we are able to show that we can see behind this type of smoke. As you could see before in the principle of active imaging, as you know the time between the laser beam and the opening of the camera, you are also able to make a 3D vision, and depending on the system that you use, we are able to make a 3D vision and to make a reconstruction of the scene for metric scene, but also for kilometric scene. So in this case, we were able in a few milliseconds to make the reconstruction of a scene of about 2 kilometers in depth. One of the applications on which we are working nowadays is the detection of UAV, and here we are using the intrinsic property of active imaging to be able to remove the background, but also the foreground to be able to follow a UAV in flight. So without the background, the different algorithm for the different tracking algorithm are very robust when they are associated with active imaging. So this was some of our different application of active imaging in ISL.